In this video, I'm going to derive the equations for calculating the acceleration of an elevator when the elevator is moving up, when the elevator is going down, even when the elevator is moving up, you might have the two accelerations. Remember, even when the elevator is moving up, you might have two acceleration. The first thing, how does the elevator work? Now let's say you step in onto an elevator and then press the button here just to go up. Once you do that, the elevator starts speeding up. Why it is speeding up? Because it is starting from from zero velocity to some other velocity. Let's say 2 meter per second, and it just takes certain time. So that means you will have one acceleration. So now let's say the elevator is moving here from 0 meter to 2 meter per second, and then it just maintains its constant velocity 2 meter per second to 2 meter per second for a certain time, and then when it is about to reach to the top floor, then it has to slow down, otherwise how it would stop. So then it will go from 2 meter per second to 0 meter per second. All right, you see here how does the elevator changing the speed. First it is starting from rest and then increasing the velocity, the 2 meter per second. That means you will have the positive acceleration. And then the 2 meter per second to 2 meter per second, that means it is moving with a uniform speed, uniform acceleration, uniform velocity. Then that means the acceleration here will be 0. And now as the velocity has gone down 2 meter per second to 0 meter per second, that means in this case acceleration would be negative. This one would be positive and this would be negative. So here the first you will have positive acceleration, 0 acceleration, and the negative acceleration. Okay, and then you should be simply able to see this value, in fact the positive and negative. So how do you do that? So you go into an elevator, take a weighing scale, weigh yourself, and just keep an eye onto this mass here, this reading here. So this reading first will increase and then it will decrease. Why does this happen? It happens because your apparent weight, that what you call as your weight, your mass, in fact is just a normal force from the ground, or in this case from the weighing scale. So as the elevator is moving up, now, the normal force does change. First when it is speeding up, when the elevator is just speeding up or moving upward, then the normal force by this elevator onto your body has increased. When you go to the top floor, then it slows down. The slowing down means the normal force by this weighing scale onto your body has gone down. So that means the apparent weight has decreased. Let's do this one mathematically now. Okay, I hope you understand here. Again, if you have any questions, confusion, just write to me. So first thing, I'll consider the elevator is moving up and it is speeding as well, speeding up too. Okay, all right. So the way you understand here is draw the free body diagram. You should be able to draw the free body diagram. So what does the free body diagram means is write down the direction of all the forces. So weight, now let's say this is your mass you put onto a weighing scale here. The weight of any object is always vertically downward because the gravity all the time is pulling it down. That's the weight here. Okay, this is the object here. It could be you, object. And again, as I mentioned, you feel your weight because there is a normal force by the ground. If there's no any normal force, if you are simply falling down, let's say from a helicopter without any parachute, that would be a disaster condition, or you simply jump off from a floor, and then now there is no any normal force, there's no ground that pushes you upward. In that case, your reading would be exactly 0. If you are now, let's say if you are on a weighing scale here, and this is you, and you let's say attach this weighing scale onto your feet and jump it from an first floor, then your reading onto this weighing scale would be exactly equal to 0, because it is not pushing you upward. It cannot push you upward. Or the other way you can think of is both you and weighing scale is falling down exactly with the same acceleration. So there is no any normal force in that case. Okay, so let's go here now. So the normal force is always upward. The normal force is here, this way here. This would be the normal force direction, because the ground or the weighing scale pushes you upward. You pushing them down and it pushes you up. That's how you get the normal force. All right. So let's call the acceleration is upward here. Why it is upward? Because the moment you press the button to go up, the elevator starts from 0 to a certain speed. Let's say 5 meter per second or 2 meter per second. And it takes a certain time t1. That means the velocity and acceleration in this case are exactly in the same direction. The elevator is moving up. Okay, the elevator, let's call this is the velocity direction, and acceleration is again up because it is increasing. All right, so that's all we need. And from this one, we can write down the Newton's second law of motion to find out an equation for calculating the acceleration. So what does the Newton's second law of motion tell you? The Newton's second law of motion tell you that the net force onto any object is equal to the mass times acceleration. And remember, this is the net force. And I can choose any direction, positive and negative. Just for simplicity, I'm choosing all the direction that is upward as a positive direction. All right. So all my upward direction is positive. So I'm choosing this as a positive direction, and the downward direction will be negative. So that means, so the normal force here is positive because it is in the upward direction. So M negative mg would be negative because it is in the downward direction. And then I have mass times acceleration here. Acceleration, of course, is positive here too. And why it is positive? Because it is in the upward direction. So A here is positive. So the rest is just one more step here. Acceleration would be n minus mg divided by m. So you can use this equation to calculate the acceleration when it is moving up. And the normal force here, so let me come back here. This normal force, this is how much reading you will see onto this weighing scale when the elevator is moving up, and that we'll call as an apparent weight. This we call as an apparent weight. Apparent weight. And why you call it an apparent weight? Because that is the weight you feel, you experience when the elevator is moving up. So this normal force we call as an apparent weight. All right. Okay. So this was one condition. Now let's change another condition here. So the second condition, this is first, this is second. The elevator is still moving up. So my velocity is still upward, but it is slowing down. And when does it slow down? When it is about to reach to the top floor, it has to slow down. All right. So now let's say exactly here in this picture here. Now let's say you started from the ground floor and then you wanted to reach to the 10th floor. Okay, from ground floor, or called 0 floor, to the 10th floor. The elevator will speed up, and then when it about to reach to the top floor, it slows down. When it slows down, what does this mean? That means the velocity decreases. When the velocity decreases, the acceleration will be negative. that in that case the velocity and acceleration will have opposite direction. So let me draw here a picture here again of the elevator. All right, so when the elevator is about to reach to the top floor, so let's say this is your weighing scale. I'm going to draw all the free body diagram. So this would be the direction of the weight. The normal force here would still be upward. The velocity is still upward, but now the acceleration here is in the downward direction. The direction of acceleration had changed. Or whenever the velocity and acceleration are in the opposite direction, that means the things are slowing down. That's how you stop a car. Okay, so now let's write down this equation here. How do I use the Newton's second law of motion in this case? So again, the basic thing is simply write down the F net is equal to the mass times acceleration. That is the fundamental equation of the Newton's second law of motion. All the upward direction is positive. So that means my normal force would be positive. So I'm simply writing down N. My weight is in the downward direction, so it will be negative mg. The one more change will be here is the mass, but the acceleration is negative. Or even if you do not have to write it down, when you calculate it will be negative, but here I can write down as a negative here. So that means I can solve for my acceleration, n minus mg divided by the negative. If you do not put the negative sign, that will be perfectly fine too. You'll get negative anyway. Okay, so just to make you feel comfortable, I have used the negative sign here. You do not have to. Well, so what's the meaning? What is the meaning? Like when I can have option either to put the negative sign, or I cannot put the negative sign. See, when you put the negative sign, that means you have defined the directions already here. Okay, it is in the downward direction. When you do not put the negative sign, when you solve actual numbers, you will get the negative sign. So in any case, you'll come to exactly to the same conclusion. All right, so this is the second case here. Now let's call it the third case here. So what would be third case? So third case would be you started from the top floor. In this case, the elevator is going down and speeding up. Okay, so let's again draw the free body diagram. So we have my weight here. What is the direction of the weight? Just mentally process everything. The question I ask, you mentally process everything. The weight is the downward. What is the direction of the normal force? Upward. All right, so that's my normal force. Now I'm speeding up and going down. What does this mean? What is the direction of the acceleration? The direction of acceleration would be here, the downward, because it is going downward and is speeding up. What is the direction of the velocity? The velocity would be again, it's going down, so it has to be downward. And the acceleration is in downward direction because in that direction, it is just speeding up. Okay. So again, let's write down the Newton's second law of motion. The F net is equal to mass times acceleration. So again, I can call all my directions, upward directions, to be positive. And you have the liberty of choosing your own direction. In fact, you can call all the downward direction to be positive. It's entirely up to you. Okay, but here I'll start this way. All right, all the directions, upward direction is positive, so it will be n minus mg, and then mass times, again it will be negative sign here. Why negative sign? Because my acceleration is in the downward direction. So that means I can solve for a or I can solve for n. So if I solve for a, then what I will get, n minus mg divided by negative m. I can also solve for n, and in this case m would be mg minus a. And I have this normal force here. See now, this normal force here is g minus a. That means in this case, when the elevator is going down and is speeding up, your weight or the reading by this scale here would go down. That means you'll feel less weight. Your weight will go down. And now let's take up of a special case. Now let's say a special case. What the special case here is? The special case here is A becomes exactly equal to the G. So what does this mean? That means this cable which is supported, so this elevator which is supported by a cable, now let's say break down. The cable gets break down and the entire elevator, including you and your vehicle, all is falling vertically downward. There's no rope now. So that means you fall down with this value G. So if I plug this equation into here, A equals to G, that means N would be exactly equal to M G minus G, that would be exactly equal to 0. So that means your normal force would be 0. The normal force, this normal force, that tells you the apparent weight. That means your reading onto the scale would be exactly equal to 0. Okay, that means you will be in a case of weightlessness, no weight at all. Okay, this is called the weightlessness condition. All right, now we have one more conditions. The elevator is going down but slowing down. Let's write down that condition too. The number 4. Elevator is going down but slowing down. So let's write down all this condition or the free body diagram. So this is my elevator. So here is my scale. So what is the mentally starts processing? What is the weight direction? The weight is the downward. What is the normal force? Of course it is upward here. The elevator is going down. So what is the direction of the velocity? The velocity is in the downward direction. But the velocity starts increasing. Sorry, it is slowing down. The velocity starts decreasing. That means as the velocity starts decreasing, because it has to finally stop down. It has to finally, when the velocity starts slowing down, that means acceleration is in the upward direction. It must be in the upward direction. Just whenever I think of acceleration, think of as a force. When the only way things can slow down when the force is in the opposite direction. That means acceleration is in the opposite direction to that of the velocity. So I have drawn all the free body diagrams here, the direction of forces. So let's write down the Newton's second law of motion. The F net, that is equal to the mass times acceleration. What is the net force here? The net force, again, I'm calling all my directions, upward directions, to be positive. So it will be N minus mg, my m times a. A here is positive. So that means I can solve for a, n minus mg divided by n. Or I can also solve above equation for my normal force, that will be mg plus a. And this is again a beautiful equation now. The n is equal to mg plus a. That means a and g are weighted together. These are added together. So what does this mean again? That means your weight will go up. Now let's say if you weigh 100 pounds, and when the elevator is going down and slowing down, your weight might reach 120 pounds, depending upon what is the value of a. Okay, so your weight is not a fixed quantity, it is a variable quantity. If you go from one place to another place, even in an aeroplane, in an elevator, your weight just change, and this is how you calculate your weight here, or the normal force. This is in fact the apparent weight. All right, so I hope you understand here. The only way you can understand better is think of yourself. And again, if you have any question, any comments, any concerns, do not forget to write to me. So this is all from this video, and I will see you guys in the class. And do not forget to like, share, and subscribe the channel.